Okay, in this video I'm going to talk about how to use the Laplace transform and inverse Laplace transform to solve ODE, ordinary differential equation. So as I mentioned in the beginning of this class, so the goal of using the Laplace transform, inverse Laplace transform, is trying to find a solution to an ordinary differential equation, which typically can be used to represent a control system. So this is is for a given control system. So we can represent the control system by an ordinary differential equation, and then we can use a Laplace transform to write this ODE. So typically this ordinary differential equation talk about in the time domain or called t domain, because it's typically given by something like if x is a state, so it's x t dot, maybe it could be double dot or something plus, let's say 2x dot t somehow plus something equal to something. So this could be our differential equation, okay, in the time domain. So by using Laplace transform, I mentioned in the previous videos I talk about in Laplace transform, you can transfer the time domain into the s domain. So what happens is you can do is L, let's see, ft, okay, use xt here. Xt is given by integrating 0 to infinity e minus t xt dt. So that's the Laplace transform. And a nice thing for the linear Laplace transform is we only got a difference equation in S domain rather than have an ODE. So I don't have derivative anymore. So it's easy to compute the solution. So once I have that one, I can find a solution in S domain. This typically should be fairly easy, because I don't have to solve the differential equation anymore. And then it comes down to, we can, once you find a solution in S domain, I can use the inverse Laplace transform to find a solution in, here is in the time domain. Okay, so that's the procedure. Okay, so here I'm going to give an example showing you how to use the Laplace transform and the inverse Laplace transform to find the solution to ODE. Okay, so here example I'm going to use. So example is I give a differential equation which is given by x double dot t plus 4x dot t plus 5xt is equal to 0, and the initial conditions are given by x0 is 1, x dot 0 is 1. Okay, as I mentioned before, so first step is I want to use the Laplace transform. This is the first step. Okay, Laplace transform of x dot t, so I do a Laplace transform on both sides. Okay, basically you apply Laplace transform on both sides. So I have L of this guy equal to L of 0. Okay, so now this, so here, because I have three different components over here, so I can use the linear property of the Laplace transform, which is the Laplace transform of each individual component. Okay, this is how I do it. Now I'm going to use the property of the double derivative of the Laplace transform, so which is given by this. Okay, if you don't know how to do it, is you can check the previous video on the properties of Laplace transform. This is for the first one. So for the second one, we do the same thing. Here we also use the homogeneity property. So which means I can put the factor scale out. So then I can use the property of the derivative to figure out the Laplace transform by x dot t. So finally I can use also the homogeneity property, and then I can put the file outside, scale outside. I can do the Laplace transform by xt. So here I assume that my xs here is L of xt. So this is just notation wise, make it a little bit simple. So once we put the initial, of course this one involves the initial conditions. I have x0, x dot 0, and x0 here. So we have to replace this one by the initial condition I already gave at the very beginning over here. So we plug in these initial conditions. Then we got an s squared. Of course I want to, for each one I replace this one by 1. Okay, so it's 1 times s. Over here this is given by 1. Similarly here, this replace x0 by 1. Now I'm pretty much done with this equation, so I just now have to clean a little bit. So I put all xs, what I do, I put all xs term to one side. Okay, so then put all the coefficients. This is coefficient 4 times s, this is 5, put them together. All other terms that are not related to xs, I put it on the right hand side. So I have negative s plus 1 and also negative 4. So I put them right hand side, it becomes positive s plus 5. Now I can find a solution of xs in the s domain is s plus 5 divided by s squared plus 4s plus 5. So that's the solution in the s domain. So as you can see from here, once you do the Laplace transform, the solution is fairly easy. We don't have a derivative anymore. So that's the beauty of Laplace transform. Now, once we find a solution, now we can use the step 2, the inverse Laplace transform. Okay, so the inverse Laplace said I just have to do the inverse of this xs. So, and try to figure xt. Okay. Now, in the previous few videos, I talked about how to find the inverse Laplace transform for several different cases. Okay. So for this one, so which case does this correspond to? So I talk about 3 cases. One is called real distinct poles, complex conjugate poles, and real repeated poles. Okay. So you want to check which case does this one fall under. So I want to first find out what are the poles. Okay. The poles is we set a denominator. So denominator, this is g of s. We set denominator to be 0. We try to find a solution. So the solution is just, we find a solution as solution is given by 2 plus or minus I, which means the poles are complex and conjugate. So it means the second case, complex conjugate. So that's the case. So we just have to follow the step in the case 2, complex conjugate case that I talk about for the inverse Laplace transform. So the step 1 says I have to write this denominator into this form, which basically I want to write gs into s plus a squared plus b squared. Okay, so this guy is relatively easy, so it's s plus 2 squared plus 1. So if you do this one, it becomes s squared plus 4s plus 4, and then plus 1. Okay, because 1 squared is 1, so it's s squared plus 4s plus 5. So that's the original one, so that's done. The second step is I want to basically write a numerator in this form, write as c times s plus a, okay, plus d times b. Okay, so s plus a here is s plus 2 because that's 1. This is s plus a, so this is s plus 2. So I put it over here. Oh, no, sorry. I put it over here. And also I want c because I only have 1, right? I don't have multiple 1, right? So it's just 1 times s plus 2. And then d times b. So b here is 1 because b is 1 squared, so it's 1. So it's 3 times 1. So if you put them together, you have s plus 2 plus 3 is s plus 5. Of course, I do one more step to split them. Okay, split them into 2 components. One is c times s plus a divided by the denominator plus d times b divided by the denominator. Okay. Now I can use the linear property of the inverse Laplace transform, which means the inverse Laplace transform of this xs, notation-wise given by xt, is the inverse Laplace transform of the individual components. Okay. So the key idea here is I'm going to use a table and a property of Laplace transform to figure out the inverse of that one. Okay. So this one I don't want to talk too much about this. You can check my previous video, which is last case. I believe of when I talk about video on the real repeated poles. Okay, so I give an example talking about how we do the find the solutions. Okay, how to use a table to find out. Basically, you use a table to find out the solution, the inverse of this individual component. Basically, if you do the inverse, you get e for the first term. You get e minus 2t times cosine t, and the second term is 3 times e minus 2t times sine t. So that's the solution. So as a recap, if I go back to the previous one, so the Laplace transform is trying to simplify the computation of the solution in the S domain, so because it makes it simple. And also, when you use the inverse Laplace transform, the steps are pretty standard, and also we can use a table and the property of the Laplace transform to actually simplify the computation quite a bit. Okay, especially when we have higher order one. Even this is a little bit simple one, you can still find a solution using the tools. So what if, for example, if I would have some very complex one, let's say I have x triple dot t plus 3x double dot t plus let's say 4x dot t plus 7xt, for example, is equal to, let's say I don't even give a 0, let's say it is t, for example, then I find a solution to fx. This can be really complex. Okay, it may not be feasible. You can find a solution in the in the time domain because it's very complex. However, we can still use the Laplace transform and the inverse Laplace transform to find the solution. Of course, the solution may be complex because the problem itself becomes complex.